So in this lecture, I'm going to discuss the basic principles of osmosis for you folks. I know you just did a brief what's it called, discussion post about this, and I want to give you a little more information after you've done research about the topic of osmosis. Okay, so osmosis, like diffusion, is the movement of something from an area of high concentration to low concentration. Okay, when we talked about diffusion, we talked about the movement of solutes, such as, we use the example of, in the lectures I've been giving, sodium. So again, if there's 150 sodium ions on the outside of the cell, if there's 5 sodium ions on the inside, okay, and we have this selectively permeable membrane, okay, i.e. a sodium gate, and we open it, you know that sodium is going to diffuse down its concentration gradient into the cell until we reach an equilibrium or until the gate closes. Okay, so that's basically diffusion. All right. Now, when it comes to osmosis, osmosis is about the movement of water. Okay, osmosis is about water moving across a semi-permeable membrane. And again, the most common example you're going to be using is cells. Okay, how does water shift around in the body into and out of tissues and into and out of cells? All right. So let's talk about this. And this can be kind of a confusing topic for people because osmosis, what direction water is going to move depends on the amount of solute within the solution. Okay. So real quickly, before I talk about osmosis, let's just review water for a second. Okay. You remember water as being H2O, right? H2O. All right. And remember, water, H2O meaning one oxygen atom, okay, that is combined with 2 hydrogen atoms. Okay, that's H2O. That's about what a water molecule looks like. All right. Now, water is a polar molecule. Now, remember, when we say polar, we mean charged. Okay, polar molecules are charged. Okay. Now, the reason why there is a charge is because there is an unequal distribution of electrons around this molecule. Okay, oxygen has 16 electrons. Okay, hydrogen only has 1. Okay, so as a result, there's an unequal distribution of electrons around the molecule. Okay, so as a result, the side with the oxygen has a negative charge. Okay, the side where the hydrogen, the positively charged hydrogens are located, is positively charged. Okay, so that means this water molecule carries a positive and a negative charge, meaning it's a polar molecule. Okay. Now, when you take a charged substance like sodium, for example, all right. Now, if I take sodium and I mix it, if I take salt and I put it in, let's just say table salt. Let's say I take NaCl. Okay, sodium chloride. All right. Now, if I take this and I mix it in some water, what's going to happen because of the weak ionic bond between these two? Okay, remember your types of chemical bonds that discussed in chapter 2 of your book. Okay, because of the weak ionic bond between this, water is going to physically force this molecule apart. Okay, so then what's going to happen are you're going to have a sodium over here and a chloride over there. All right. So then, now remember, water is polar, right? And remember, when molecules come together, you're talking about electrons coming together, right? Okay, so what's going to happen is free water molecules are going to surround this sodium and the chloride ion. Okay, now sodium has a net positive charge, so as a result, the water molecule is going to look like this. So let's say this big circle is the oxygen, and then these are the hydrogens. Okay. All right, so this would be the oxygen, which is negative. Okay, and these would be the hydrogen ions, which are positively charged. Okay, so as a result, the negative pole, the negative end of a water molecule, is going to surround the sodium side of this, the sodium ion. Okay, and then over here, with this chloride ion, you notice the exact opposite is happening here. Okay, the positive pole, where the hydrogens are going to face towards this negatively charged chloride ion. Okay, so as a result, what's happening then is as these solutes are mixed in the water, all right, the normally free water molecules within, let's say, we're looking at a beaker here. Let's say this is a okay, so let's say this is a beaker of water here, all right, and I just dump some table salt in there. All right, this is what you're going to be seeing. All right, so the sodium is going to be separated, and then the water molecules are going to, engulf the sodium, and the negative pole of the water molecule is going to surround the sodium. Then you've got the chloride, and then bam, the hydrogen end is going to face, chloride. All right, so now as a result, there is less free available water molecules in this beaker than there was before I added the sodium, because if we don't put any sodium, any minerals, any proteins, we don't put anything in there, all right, the water molecules are not going to be bound to anything. They don't even chemically bind to these, but because of the opposing charges, all right, there is a chemical attraction between the two. All right, so that means there's less free available water in this beaker. All right, so let's kind of do a little. So let's say I've got beaker A and I've got beaker B. All right, let's say both of these beakers have 500 mils of H2O, 500 mils of water within them. Okay, now in this beaker, in beaker A, let's say I put in 2 grams of sodium chloride. Okay, and then in beaker B, I put in 7 grams of sodium chloride. Okay, which beaker is going to have less water in it? Which beaker is going to have less water in it? Take a second to think about that based on everything we just discussed. The answer is B. Okay, there's less water in B. Okay, because since there is more sodium and more chloride in here, that means more water molecules are going to be occupying these ions in here. Okay, so that means there's less free water in here. All right, so basically you're noticing kind of a reciprocal relationship here. Okay, as basically as the concentration of this solution increases, so we'll say as we increase the number of solutes, okay, the volume of water decreases. Okay, so the more solutes, the more ions or solutes that are polar that you mix in water, the less free available water there is. Okay, so now let's say I take a connecting membrane, all right, and I attach these 2 beakers together. Okay, you now know that there is not an equal amount of water, okay, between these 2 beakers. All right, so as a result, what direction is water going to travel? Take another second and think about this. Okay, is water going to travel from beaker B to A or A to B? Think about this for a second. The answer is going to be water is going to shift from beaker A over to beaker B. Okay, because there are more free water molecules in beaker A than there are in beaker B. Right? Remember what I just said. Okay, as you increase the solute concentration, the water volume goes down. Okay, so that means there is more water in here. All right, so as a result, water is going to shift over to this side. All right, water is going to shift over to that side until you reach an equilibrium amongst the concentration of water. Okay, so this is still a passive process. All right, all there is just a difference in the amount of water. There's a concentration gradient, and water is shifting from high to low. Okay, So let's put this in practical terms. Let's put this in let's talk about how this